So the goal of today's video is to use a multilingual model to do question answering or to generate embeddings. A BERT-based model is fine, but not the Roberta one. Maybe the Robert is the Dutch variation, or maybe just a different one that supports multiple languages. So that's exactly what I did in this notebook, the next one. There are links in here from the ONNX runtime to guide you through all the steps to do to export a model from Python using the transformer libraries or other, and then using that exported ONNX model in your C# to use. So I'll show you the documents later, but if we quickly run this one, and the point is to illustrate as well that this English model does not perform well on Dutch language. So these are English samples, just the same ones, training inputs. But I'm not really training the model, if I'm not mistaken. I'm just using it as is. And then I have some Dutch samples. Similarly, where does Nelson Mandela come from? Why are bananas bent? Why are they shaped like they are? And why to use DTOs instead of domain model? So this is an English one, simply to quickly see the difference. This is a custom implementation. I will go over the docs later using a custom BERT tokenizer package and the ONNX runtimes. I will, on these, there's multiple tokenizers here, German, multilingual, and so on. But then you need to also use a German or multilingual model. So that I haven't done yet. This is simply tokenizing. Oops. Oh, I didn't execute this. So simply tokenizing, splitting the sentence up into tokens. Some CLS, forgot what it is, start of line or something. Some, because this is JSON serialized, basically containing what the input expects is a question and the context. And that needs to be serialized as a JSON string. So you'll see those brackets being encoded as well. Then the question key, then the actual question, and then the context key and the context encoded. That's probably the IDs for each token. Yeah, like that. Get all the IDs. Or what? Let's see. Okay, then the specific input to be used, shape to be model input for the BERT model, input IDs, attention mask, and type IDs. These are things that the Microsoft official APIs abstract away for us, so we don't need to worry about these kind of things. But this is all copied from the ONNX documentation, so it's not like I have to, and this is based on how they interact with the BERT model in Python using PyTorch, the transformers library. Then I'm preparing the inputs. Then I'm loading the model path. I will show you this would need to be exported using some Python code. I will show you that in a bit. But this is the BERT large uncased. So uncased, I mean, if I'm not mistaken, it had something to do with text casing. Uncased meaning there's no casing. I'm not mistaken, whole word masking fine-tuned squat. Apparently this model should be trained, fine-tuned to do the question and answering task on thousands of sentences, maybe millions of question and answer samples. Then this is a bit awkward code using, basically creating tensors and disposing them afterwards in memory, from memory. Basically also preparing the inputs, the attention mask, the type IDs. If you go further in using BERT models, you'll bump into that input. And then this inference session, this got stuck on other package versions. So this is the loading the model, and then we're passing the inputs where we run the model. So we do the inference run. Then the outputs should contain the answer of on the question. This is some code to post-process, as they call it, the output of the model. And then, let's see. So it basically answered DTOs doesn't need to map one-to-one models. It seems like this is maybe a tokenization issue. But it basically gives the entire sentence as answer, while it should only be the last part. But it's not too bad. Let's try a different... So that was the English sample. I could say training inputs and have the typical Dolly Parton one, or the Bob Dylan one. This is Bob Dylan. And then it should say Duluth, Minnesota. This is lowercase, some weird space, but okay. Pretty good answer. If I then try a Dutch sample, just for testing inputs, I think it's first. It just gives me CLS. So then I had to figure out how to use a different model. So there may be multilingual models that I could plug into this, export it first from Python and then plug it into here, this code base. But the tricky thing is, let's say we try that for a Roberta model, which is more modern than this one. Then perhaps we need to figure out, well, follow a different guide to prepare all these inputs, possibly. But this code we'll see later on. We'll see it in some kind of package I want to cover later, a NuGet package, which has already done the work for us. But for that, let's first take a look at the model. So this ONNX model is, if I'm not mistaken, it's pretty heavy. It's about 1 gigabyte. If I'm not mistaken, yeah, pretty large thing. Then we had to get some vocabularies as well. Let's see. For the tokenizer. So to accomplish what I just did, you can just simply follow these links. There's even a video, but this is, I think, slightly more outdated. Let's get the Python sample. Let's show that for a second, which is also documented in these links. Let's see. It's already here. I just used this already existing Python project because it already has the virtual environment with all the packages installed. And then this is the notebook, added the links. I will likely provide it to you on my Patreon and gizcodemembers.com, the gizcode.com/members section. Let's see, so this is a little bit of code importing TorchSharp and then the transformers library, and then specifically the model, the BERT for question answering. Here, Torch CUDA seems to be available for machine learning, deep learning. Then we just specify the model name, which is the same one, encased, BERT large encased, word masking fine-tuned squad for the question answering. And then I'm exporting it, the model path. I'm going to export it to a folder in my project. We're loading the best BERT for question answering model, so the pre-trained model. We just check if everything loaded well. This is the structure, which may be a dropout layer. We may learn about that later on. Then some dummy inputs, so that those input IDs, the attention mask and the token type IDs, which we saw in the C# as well, the dimensions and so on that the model expects. So, and then we simply export that model. These inputs can change depending on model and task. That's what I got from the video. So I can't simply, maybe I can, but we'll have to see. I can simply use the Robert model and assume it's then be just fine. Or if it's a different task, like there's like a multiple choice generation task, then this could likely be different. And then the code that follows, so we already have the ONNX model now, so we simply can copy that model, which is about 2 gigabyte. We can copy it to our C# project and then use that using the code on the links and in the notebook that I showed before. And then simply the steps to test out this model, to try the model for question answering. There's some pre-process, post-process to get the inputs ready and then the outputs ready. Get from whatever the model outputs to a decent human readable answer. And then this is basically the inference run method, expecting those model inputs, creating a session and running that session. So the outputs, then run those outputs through the post-process to get a decent humanly readable response. And then we've got this init function, which basically needs to be run before the run to load the model, the pre-trained model. But this time it's loading it from our exported folder. So the steps we did above. And instead of from the transformers library. And the model and the session tokenizer will be initialized after running the init method, and only after we can do the run method. Okay, and then we see answer Rebecca. So we simply wanted to test the model. So this is basically now the way we should go around the out-of-the-box Roberta models that the official APIs of Microsoft provide. Awesome people that have already made some NuGet packages. But while I'm on the YouTube page, if you want to go through those Python code to export your own ONNX models, I already showed you how to do that with the YOLO models, which is this video about a year ago, setting up the Python environment, installing the correct packages, which in that video is Ultralytics and Transformers, if I'm not mistaken. And then we simply export an ONNX model to be used in C#. That brings me exactly to this YOLO Sharp. This is then the package that I bumped into that we can easily, this is for computer vision, for object detection and so on. And this also shows how to export it. So that's the Python code, but then you can add the C# package and basically just start using these exported YOLO models easily by just passing the path to your local model and starting to detect or predict. So then that brings me to the next awesome package, is this one. This is for your NLP tasks. Well, actually for generating embeddings, but this is using a model that supports more than 50 languages, so multilingual finally. Based on the sentence transformers. Also, these models can be exported from Python or even just found in the repositories on the Hugging Face. And it works quite similarly, using the model and to generate an embedding. So for this example sentence, but we can use our own models, so a different one. But there's only like 2 models supported, I think. And that's this All-Mini LM L6, but also the L12, which the L12 I think supports more languages or more embedding, larger embedding space or layers or whatever. So you can pass the model path and you can pass a vocabulary using a BERT tokenizer, so BERT-based model, and then generate embeddings. I tried this, works really well. Bit confusing, includes tokenizer and model, an ONNX model, but then the NuGet does not include ONNX model or the vocab. If you go to the source code of this, the source repository, you will see that's over here. You will find in the model folder the ONNX model and the vocab. Let's have a look. But hopefully it's not included in the NuGet package because these things are quite heavy, especially the model. It's about, well, it's at least more than 100 megabytes. The cool thing about this package as well is I was curious on how he does it, and it's basically using similar code as on the ONNX documentation. So using this ONNX runtime values to create the tensors, then prepare the input for the BERT model, run the inference session, then apply some, let's say, post-processing steps to then actually get the embedding as output. You can also generate multiple embeddings. A really cool package, all mini LM. I have tried it out and it works really well. But in the meantime, I already kind of cracked my case by using, I think, the Glove embeddings. Let me see, ml.net embeddings over here. I basically found some pre-trained models from Glove. And then I looked at the fast text, but I didn't find anything. And the Gloves one were more recent, like from the year 2024, and the fast text of 2019 or something. So I just went here to this website and then got myself a download of, if I'm not mistaken, these are called like static embedding models. BERT models are called dynamic ones. Let me tell you more about that later. Anyhow, you go to this website, let me zoom in. And then you find, I took the smallest one because this is already like 290 megabytes. That's quite a lot. But you just basically, it's got like 11, almost 12 billion tokens, 1.2 million vocab entries, it's uncased, and 50 dimensional vectors. And then you see the bigger ones are like 1.6 gig. Glove is an unsupervised learning algorithm for obtaining vector representations for words. Training is performed on aggregated global word-to-word co-occurrence statistics for a corpus, and the resulting representations showcase interesting linear substructures of the word vector space. So let's quickly look at this AI overview. Static word embeddings like word2vec in Glove assign one fixed vector to word, failing to capture context, bank, finance, while dynamic contextual embeddings like BERT generate unique vectors for a word based on its specific sentence, more contextually aware. Effectively handling polysemy, which just means that there's a lot of words with multiple meanings in different contexts, have different meanings, capturing richer meaning, making them more powerful for complex NLP tasks, but computationally intensive. So static words embeddings, so there may be a little less on nuanced scenarios, and then dynamic ones, BERT, GPT. But what you also notice is these vector spaces are way bigger, like you saw in the llama. The length of one vector was like 4096. But then all the progress they're doing on models like GPT and LLMs, large language models, and so on, after a while they find techniques to improve the static embeddings as well. So that's why new 2020-24, I've been using this one for now, the smallest one, and this is 2014, so I'm not inclined to use that. So, but those most recent ones, they seem to perform decently on my use case, which is a simple use case. It's basically I just want to catch similarities between dog breeds that are slightly differently spelled. And if I take a look at the result, so basically, let's go with the code. And the cool thing about this is the Microsoft APIs already support this to use word embeddings, and even then to go look for the more recent Glove embeddings or fast text embeddings. Some links at the top here that will show you how to do that. Yeah, let's just get the ML packages, model input, model output. We don't really need to train this thing since these are pre-trained things, so we're just using some empty training data, so to speak. And then this is the transformer pipeline, which is ml.net that supports this. We're basically, so I followed the Microsoft sample, but tokenize into words, so the dog breed name into tokens, and then apply word embedding, output column name embeddings, input column name tokens. And then I'm loading this custom model file, which is basically this Glove what was it, 290 megabyte file, text file that I'm loading, which is basically the model, pre-trained model. And then you could use some out-of-the-box ones, fast text Wikipedia, but I failed to load that in my notebook because it's not like it stores it on a different place, downloads and stores it, or can't download it because it's too large. Anyhow, can load a custom one. I didn't load it in the project since it's that large. I didn't want to push that to GitHub. So, but it's that. The links are at the top. So training on empty data. So because we don't really need to train it. And we're simply using it as prediction engine. Then our cosine similarity methods to measure similarity, and we're going to load in the breed responses, the dog breeds with their aliases, have an embedding response, have the code to read and write the JSON file. So the write was basically to update this file with each breed and each alias's embedding. But these embeddings, for the llama at least, the llama model, they were huge. I tried that, and the file went from a couple of kilobytes to 60 megabytes because those embeddings with each of a length of 4069 became quite heavy for about 100-ish breeds, and then plus the aliases, maybe 200 data records. So I can imagine storing these embeddings, which is probably necessary for RAG systems, storing these embeddings in the database for 1 million records. It's pretty crazy. Just simply looking at the breeds, then doing a test prediction. So cat and dog, you see these embeddings are only 150. The size is only 150, so that's quite a bit smaller. Then the cosine similarity between cat and dog is pretty high, 94, because they're both pets likely. The feline and the canine. Then for each breed, I'm kind of getting the embeddings, preparing all the embeddings. So for each breed and all the aliases, preparing the embeddings to then do some kind of similarity search on. So we want the top X amount of closest, most similar breeds to the search inputs. So we start retriever, then pitbull, misspelled with 2 T's. That's a miss thing. Then American, just to see what it's going to match with. Flat coat retriever or flat coated retriever, I think, to see what comes out of there. Then Dogo Argentino, misspelled. And then a multilingual example, a Dutch example, to see if this is going to find anything decent. And then we're basically looping over the search inputs, creating an embedding for each search input, because we need to compare them to all the embeddings, so for all the dog breeds and aliases, and simply returning, lowering the scores. So, and I'm pretty pleased with this already. So for retriever, we've got flat coated retriever, flat coat retriever, Labrador retriever, even Labrador. It's quite amazing. Retriever and golden retriever. So this means it really understands the semantic meaning of retriever, that it's some kind of dog breed and close to either the Labrador, the golden, and so on. The scores are pretty high, 90, almost 80, 60, 76. It's pretty good. So we would likely want the golden retriever to be at the top, but okay. Maybe it's more a fine-tuning case, perhaps. Then the misspelling of pitbull, that didn't give me anything, which is unfortunate because I expected it to find the correct spelling of pitbull at least, which should be among the breeds. But these are all low scores. So if this happens, I will just ignore it, I guess. And add it to my aliases later. Then American, the first thing it found is American staff, which is French. That's cool. Multilingual, 84, pretty high probability. Then American staff in English, 84. American Bulldog. Flat coat retriever, so the first thing is itself, flat coat retriever, and then it has, no, flat-coated retriever, even better. This is actually what I wanted, but yeah, the scores are the same. So flat-coat retriever, Labrador retriever, pretty good, Labrador, and then golden retriever, all high scores, really good. Then the tricky one, Dogo Argentino. Well, it's present in the database, so it's just finding itself with a score of 1. But let's say it wasn't in the database, the first result would be Dogo Argentino, which is pretty good. The score is not the highest, but yeah, 67, it's pretty good. Then it finds Argentinian Dogo, 60%, Argentine Dogo, and then yeah, German Spitz dog, Dutch Spitz, that's not relevant. But the first result is actually the correct spelling of the Dogo Argentino, so this is pretty good. This validates that this could work for to tackle my problem. And then we've got Argentijnse Dog, which is the Dutch translation for Dogo Argentino. First, of course, it finds itself, Argentijnse Dog, Argentijnse Dog. Then it finds the Danish dog, which, yeah, could be understandable why, but it's not what I wanted. Then the ex-pitbull for some reason. And then only then it finds the Argentinian dog. At least it does find it, but not the best score. So this is lacking a little bit here. I couldn't really find if the GLOVE dataset was, well, the GLOVE model was trained for multilingual use cases or tasks, but yeah, it is scraping all kinds of Wikipedia pages in all kinds of languages. So, and it seems to perform pretty well on even finding French, and but yeah, maybe that's just a coincidence since the writing is almost the same. But it seems to do decent on multilingual cases or misspellings and things like that. It does seem to match Argentijnse Dog and Deense Dog, which is a bit too high, but okay. Then we're going to compare this static embedding, which was about 290 megabytes. Should probably verify it in my folder, but anyway, it's 290 megabytes. And then now we need to compare it to the dynamic BERT-based embedding model. So we've got the same code here, we're using that NuGet package. Well, this is all the same, loading the breeds, loading it from the JSON file, showing some breeds. Then we're using this all-mini LM6 package because that seemed to be supporting 50 plus languages and so on. This L12 is going to be bigger than the 6, but the size was pretty decent. It was like only 130 or 160 megabytes. But then you have the vocab as well file. So let's take a look. So the link to the NuGet package is there, where to download the vocab and the model. Here are those two links at the bottom, tested models, the L6 and the L12, and that goes to the Hugging Face. So the L12 is what I'm interested in. Then you basically just go to Files and Version. Files and Version. Then you can find the ONNX model in the ONNX folder. And you can find the vocab.txt in here. So this has been updated 4 years ago, but the ONNX model about 1 year ago, and it's only 133 megabytes. Let's check the vocab. It's only a couple of kilobytes. So in terms of size, that seems to be pretty good. We do have to load all the TorchSharp, well, this package in the TorchSharp, and hoping the model is not included in the NuGet package as well, because it would load twice. Okay, just using the package in the tokenizer. I just downloaded the vocab and put it in that same embeddings out of my GitHub repo, so it wouldn't be uploading all of that to Git. Then the ONNX model, then it's simply, yeah, the notebooks require me to use these using statements like this, so I can't use the one-line notation. That's why the other code was so nested and awkward. Then this can generate embeddings multiple at once, so cat and dog. put them into arrays to then measure the cosine similarity. Now this is only 53. Let's see, what's the length? So this package, oh, it's installed, yeah, it's cached. Took 23 seconds before to download this one. Okay, so the size of these embeddings are 384 for one embedding. That's more than twice of the Glove one. But the results are actually way better. So again, search inputs are top similarity function. Then we're using this, the using statement, and having to do everything inside of there, which is a bit awkward for these notebooks. So just adding the embeddings to all the BERT and the aliases, preparing the all embeddings collection to then compare the search inputs after generating embeddings for the search inputs, which we could maybe do in one line using the generate embeddings. But basically getting the embeddings and then the cosine similarity between the input embedding and all of the embeddings, and then logging the similar results, and these results are pretty good. The scores, let's see. Retriever, taller retriever. The score seems a bit lower, but it even gets the Nova Scotia retriever out of here, which we should have expected in the other one as well, but it wasn't there. But we also saw the cat and dog similarity was quite low, so maybe this is just less accurate or something. Well, don't know how to say it, but maybe just all the scores are lower in general. Then this is marvelous. Pitbull, misspelled, compares it to Pitbull, correctly spelled. This is what I was hoping for in the other one as well, but it didn't come out. Then it's got Poodle for some reason, so this is almost 70. And it's got American Pitbull Terrier, Amerikaanse Pitbull Terrier, so multilingual, but yeah, it contains Pitbull. Should be more at the top, there's a low score for that. American gets Akita, Bully, Stafford, Cocker Américain, which is a French name, and American Bulldog. Decent scores, well, not really high, but Flatcoat Retriever and Flatcoat Retriever, slightly differently spelled. 98.8, almost 99. Flatcoat with flat-coated, 91 almost. Flatcoat Retriever, flat-coated Retriever with the dash. What's the difference here? No, it's the same. No, the dash here. Between that and that, but the same, almost the same score. Then the Flatcoat Retriever and the Labrador Retriever, pretty high, is okay. Dogo Argentino with itself, the misspelling, this should be eliminated in the database. Then the correct spelling, 90, which is pretty awesome. So Dogo Argentino, correct spelling with the misspelling. And then we've got Argentinian Dogo, which may be just English, but the words order swapped. 0.85, pretty high. Argentine Dogo, maybe another variation, alias of the breed. 80, Dogo Argentino and Argentinian Dog, which, yeah, all just differences. Argentijnse Dog with itself, okay. And then it finds all the aliases for Argentine Dog, for the Dogo Argentino, which is pretty awesome. This is performing better than the static embeddings. Also NuGet package, and the code, as we saw, was a bit similar as the ONNX code, which is basically this runtime documentation for .NET 6, if I'm not mistaken, supporting all kinds of BERT, multilingual, German, and so on, using a tokenizer which comes from a different package, open source package from someone else. And that's could do the question answering. And if you see, this is the Python code that I showed in the notebook. Then some testing with the Python model just to see if everything worked fine. And then trying to get that model into C#. Even the versions are here. And if you see, it's the same code with input IDs, attention mask, type IDs, preparing the inputs, well, tokenizing, encoding, preparing the inputs, then creating tensors, and run the inference before we can get our answer after post-processing the model output. That's basically a bit the same as the code in here. The embedder followed the same source, possibly. All these tensors preparing the inputs for running the inference session, and then post-processing the outputs. Let's then quickly go to another source. I did cover this, or briefly showed this in the previous videos too. Basically semantic search, but he also went the route of loading a custom DistilBERT MS Marco database dataset model based on MS Marco dataset, which contains a lot of Bing searches, if I'm not mistaken. A whole lot. So he converts that specific sentence transformer model to, which the sentence transformers is also from the Hugging Face package that this one uses. And then he has, well, the GitHub repo is also available, but he uses this apply ONNX model. So maybe that's something, another approach we can take to, and he has to prepare all these inputs, which are basically the similar for a BERT-based model, are those input IDs, attention mask, creating those tensors for that. Input IDs, attention mask. We don't seem to have the type IDs this time, so these can slightly vary based on the models. And then what I assume is some post-processing. And then the cosine similarity code using tensors. And basically to get, to generate embeddings and to find the semantic search, so the similarity search between, which is quite between query tensor, which is the embedding for the query, and the embedding for the corpus normally. You can find the GitHub as well. I tried to find if this supports multilingual cases, but it wasn't clear. It said because MS Marco is trained on those Bing searches that it's likely multilingual, but it's still English-centric. Godito.in. Pretty cool stuff. So maybe an alternative approach to load, use ONNX models. Because we're not out of the woods yet. Now we have this way of generating embeddings. We have that way of generating embeddings, and we can just do it ourselves as well. But yeah, it's similar apparently for the question answering as for the generating the embeddings. It's likely the output is likely processed differently. But now I have to find a way, so either using one of these approaches to crack my named entity recognition case, because after adding plenty of data, I think we've got what, almost 6,000 records, and I labeled them better. So these multi-token entities, you basically can label them according to the BELU format, which means this is the first token that makes up the age. This is an inner token that makes up the age, and inner, and then the last token that makes up the age. If it's just a single token, you can say, okay, it's just a single entity token. You use the U. If it's a non-entity, you use the O. So you basically have the below structure. Anyhow, the results are unfortunately still horrible. And I'm starting to think that it's simply because I'm trying to do this using the Roberta model, which is an English-centric model. So this is basically name, Joske, age, 7 years and 5 months, sex, male, breed, Labrador, and then I added the dummy just because of the offset issue. So it's got, so the first one is part of the offset issue. So it's got a non-entity name, which is good. Then Joske be name is really good. Then another non-entity, which means the label for age. And then it starts detecting the age, 7 years and 5 months. 7 years and 5. So I don't know if he dropped the end or something, but I'm basically missing the last token, which could be crucial. Then a 0 non-entity. Well, actually is detecting this as non-entity now, these months. Non-entity for the breed label, and then the usex for the sex. Usex, he finds it. It's a single entity. And then breed, which is wrong. This should be a non-entity. And then Labrador breed, this is correct. But ideally, you get it on a more random text, not as much in line as with the training data. So that's not so good. And this is all Dutch text. So I'm starting to think I need to find a way to get to use a BERT-based model for named entity recognition, pre-trained for that task, and being multilingual. Or find some kind of BERT-based multilingual base model and somehow find a way how to fine-tune it or train it for this specific task. So that's going to be a challenge for, well, I'll make a video if I ever find a way how to do that, but I do really need to do that to crack my case. Okay, so I'll leave all of these notebooks. I'll drop them on my qiskit.com/members section. After becoming a member, you can download all of that, everything, or on Patreon, where you can access everything, and everything from the machine learning and deep learning videos that I produced, but also more from previous videos. Don't forget to like and subscribe, and see you next time.